Welcome everybody to Calculus BC. In today's episode, we're going to be discussing chapter 9.4, which is the comparison test. And this test is actually quite different than the rest, in my opinion, because this one definitely calls upon us to rely on our own knowledge more so than the other tests that we've seen in the past. And so the way I'm going to describe the comparison test is actually through a lot of comparison. And so what we've been doing up until this point here with convergence testing is we've been doing a lot of comparisons between sequences and functions. In the integral test episode, we saw the summation of a series and how it behaves the same as the integration of a function. And so we've been doing a lot of comparison up to this point. And so the ultimate in comparison tests will be to compare a given series with a series that we actually already know. And so in this case here, the reason why the comparison test is different is the comparison test is basically finding convergence by having a hypothesis and then comparing to a series that we already know, or rather a series whose behavior we already know. Okay. And so from here, what I'm going to do is I'm going to begin with a series here, and I'm going to begin with the summation from n equals 1, from n equals 1 to infinity, of 1 over rad n minus 1/2. Now from here, again, the reason why this is difficult is because in this case, we need to have reasonable suspicion of what's going to happen here. So if you want, take a second, pause the video, see what you suspect is going to happen here. But we should hopefully suspect that this thing is going to diverge. And at this point, hopefully this series reminds you of something else. And that is where the comparison comes in. What we're going to do is we're going to compare this. We're going to compare this to the sum from n equals 1 to infinity of something that you want to keep your comparison as close to the original as possible. My general way of thinking of this is try to keep it within a vertical shift or so. You don't want to be comparing it to something totally crazy because at some point you're going to be seeing what their behaviors are. And ultimately, that is the crux of the comparison test, is to understand, does the behavior of my series that I chose, is that the same as the behavior of the series that they chose? And if they are, then they would behave the same way. And so what I'm going to do is I'm going to go ahead and compare this to 1 over rad n. And I chose this 1 over rad n because it's very close to the 1 over rad n minus 1/2. There's just no minus 1/2. If you think about plugging in values of n, as n gets super, super large towards infinity, that 1/2 isn't going to matter anymore. So hopefully it makes sense why I would compare him to a more simplified version of himself. And so the reason why I chose this also is because if I look at the sequence generators all on their own, like this, I might be able to determine which one is larger and which one is smaller. And so the reason why that's important is because, well, first off, let's just go and establish which one's larger. This might be a little bit counterintuitive, but actually the 1 over root n is the smaller of the two. And let's talk about why for a second, because that actually in and of itself could be a lesson in and of itself, because it takes a lot of number sense, and I'm sure you all have it. It takes a while sometimes to kind of see it happen. We see more things happening in the denominator of the right side, which means we think it's larger. But actually, because we're subtracting 1/2, this is what I consider to be, and I'll go and type this out, that way we can get in our notes more cleanly, a smaller denominator, meaning an overall larger number. So hopefully that makes sense. Now, why is this important? Well, if we think about it in terms of a position perspective, if we look at both of these graphically, I'll go and do the 1 over n as a sequence, and then 1 over rad n minus 1/2 as a purple sequence. If I was to look at 1 over rad n minus 1/2, right? If you were to graph this sequence, you would find that it kind of behaves like this. But if you were to look at the position of the other one, of the one that we chose, the 1 over rad n, it would be slightly underneath those points. It'd be slightly underneath those points, because the numbers of the white dots are slightly smaller than the numbers of the purple dots. Now, if we know the behavior of the white dots, that they're going to diverge, meaning their summations are going to shoot upward, right? They're going to create a sum that does not converge. Hopefully it makes sense that the behavior of the purple dots, or the pink dots, would behave in the exact same way, because if one is smaller and shooting upwards into infinity, then the larger one, as long as the behavior was the same, would do the exact same thing. And so what I'm going to do is I'm going to go ahead and define this summation here. Since we know its behavior, I'm going to go ahead and call it something. I'm going to say this is a divergent p-series because p is less than 1. And because we have established the behavior of our comparative series, that means that the series given, as long as we knew for beyond a shadow of a doubt that the given series was bigger than my created series, let's say for all n greater than or equal to 1, then we could conclude then by the what we call direct comparison. Direct comparison. The sum from n equals 1 to infinity of 1 over rad n minus 1/2 also diverges. Again, what we did was we compared the series that they gave to us to a series that we knew. And we knew that the series diverged upon its end behavior, which means the series they gave to us had to have behaved the same way. Hopefully that makes a lot of sense, or at least enough sense. I'm going to move on to the next example. Give me a second. So in this next example here, we've got the sum from k equals 1 to infinity of 1 over 2 to the k plus k. So again, when it comes to these direct comparison tests, all of these comparison tests, we want to have reasonable suspicion as to what this is doing. So what do we suspect? We suspect that hopefully it kind of reminds you of something, right? I mean, hopefully we suspect that this thing is going to converge. And the reason why I think this thing looks like it's going to converge is because this almost looks geometric, right? Geometric looking. So now what I'm going to do is I'm going to go and create a geometric series that is very similar to this that I can use to directly compare it to. So in this case, I'm going to say, let's go ahead and compare. Let's go and compare this to, again, I always choose as close in line with what I have as possible. I'm going to go ahead and choose something more simple than this. I'm going to call them the sum from k equals 1 to infinity of 1 over 2 to the k, without that plus k on the inside. And so again, what do we know about this thing? This is a geometric series, a geoseries, that converges. And I have to say why. I have to say because the absolute value of r is less than 1, right? This could actually be seen as the sum from k equals 1 to infinity of 1 over 2 all to the k power. And so now what I'm going to do is I'm going to go ahead and compare the two in terms of magnitude, which one's larger here. So I'm going to say 1 over 2 to the k. Well, how does he compare to 1 over 2 to the k plus k? Well, in this case, again, which one has the overall larger denominator? This guy has the overall larger denominator on the right side, making him the smaller number, meaning that my comparative function, unlike the last one, is actually larger. So in the last example, when we had the larger denominator indicated divergence, right? But in this case, we have a larger denominator, and I want you to pause for a second and think, is this a good thing, right? Because this is opposite of what we had in the last example here, right? Now, is this a good thing? Well, I would suspect that it is. And this is a good thing. This is good. Good. Why? Well, because we suspected convergence, right? And if we think about the opposite of what's happening from the last example into this example, right? What we have is we have a series of pink dots, and again, if I was to go ahead and graph the given sequence in pink again, what would happen is they would probably behave something like this. Now, the white dots are actually above them, which is actually a good thing because we suspect that those white dots are going to plunge downward into convergent land. And if they plunge downward into convergent land, that means that they will take the pink dots with them. So that's a good thing, right? So we want that to be true. This is true for all k greater than or equal to 1. And so since we know that this is true here, what we can do is we can say, all right, well, because we suspected convergence on the series that we're comparing it to, that means that the series that they gave to us, must also converge, right? So this guy must also converge because of direct comparison. So direct comparison actually takes quite a bit of thinking, but it doesn't take a whole lot of work as long as you have reasonable suspicion that's accurate. So hopefully that makes sense. I will come back in a little bit with this thing being defined here. So in the last couple of examples, I showed you one that diverges, one that converges, and I had to show you the location of our comparative series with respect to the given series. And so hopefully I'm going to go ahead and summarize that idea in just a second here. And so what I'm going to do is I'm going to say let the sum of a sub n be the given series, and I'm going to let b sub n be the comparative series. And the way direct comparison works is if the sum of b sub n, in other words, if our comparative series is convergent and our comparative series is larger than our given series, then the given series a sub n must converge. Again, we're talking about same behavior, right? And so the other one is going to be if our comparative series is divergent. And in this case, the comparative series must be smaller than the given series. Then the given series must diverge. And again, we saw that in the last two examples, right? In this part A, this A part of the definition is what we saw in the second example, right? We saw a comparative series that was larger, so therefore a comparative convergent series that was larger, so therefore the given series had to converge. In this part of definition B here, we saw that our comparative series diverged and was comparatively underneath the other one. Then the given series had to diverge as well. So this is direct comparison defined. Give me a few seconds. I will come back with the next type of comparison test. Give me a second. So let's take a look at this example here. We have the summation from n equals 1 to infinity of 1 over 2 to the n minus 1. Now this one here is actually quite similar to the one that we had in the last example, except this time it's actually being subtracted by 1. It's being subtracted by 1. And so let's go and find out something that we can compare it to. We can go and compare it to something else that we know converges, because we should suspect that this thing converges. Now what we're going to compare him to is probably, again, a more simplified version of himself. Here's the problem with this comparison, though, is that if I compare 1 over 2 to the n versus 1 over 2 to the n minus 1, the issue is that because the guy on the right side has a smaller denominator, he's overall a larger number. And so unlike the definition that was just given to us, we can't be underneath a convergent series and pull him down with us, right? We saw that the convergent series has to be above the series in question. So that makes this problem a lot more difficult. Nevertheless, we are actually going to compare to this 1 over 2 to the n, which is a convergent geoseries. And again, that's because the absolute value of r is less than 1. But when it becomes difficult or even impossible to tell which function is above or below, or if one function isn't clearly above or below at all times, we go to a different kind of comparison test, which is called limit comparison. Now, limits are a really great tool for comparison testing because limits will often tell us the end behavior of the functions that we're looking at. And so the way limit comparison test works is, in general, if I take the limit as n goes to infinity, if I do that of a sub n over b sub n, again, with a sub n being the given series, and then b sub n being the comparative series. And again, we're just going to take the limits of the sequence generators here. If I get a value c, all right, if c is positive and finite, then that means that a sub n and b sub n will behave the same way. And in this case, because we are comparing our given series to a convergent series, that would mean then that if I did the limit comparison of this particular series here, I would end up with both series behaving the same way, in this case, heading towards convergence. So that's what I'm going to do. I'm going to go ahead and divide the given series by the comparative series while taking the limit as n goes to infinity. I'm going to see what happens. The limit as n goes to infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n, which is going to be the limit as n goes to infinity of 1 over 2 to the n minus 1 times 2 to the n over 1, which is the limit as n goes to infinity of 2 to the n over 2 to the n minus 1. Of course, as n goes to infinity, these guys are your dominant terms right here, which means you'll have a totality of 1. Now, this 1 is positive and finite, which means that the behaviors will be the same. How do I know? Well, if I was to look at the limit for a second here, the limit as n goes to infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n. If I was to say that does equal 1, one way we could look at this is I could multiply both sides by 1 over 2 to the n, which means the limit as n goes to infinity of 1 over 2 to the n minus 1 will get us 1 over 2 to the n, essentially, right? The behaviors will be the same. And if the behaviors will be the same, that means that the behavior of the summations would be the same, just like we saw in the integral test, just like we saw in direct comparison. So again, a lot of comparing going on here. So we've got positive and finite, so we can say, therefore, by limit comparison, the sum from n equals 1 to infinity of 1 over 2 to the n minus 1 must also converge. Again, we've got a known convergent series we established. We did the limit comparison, which means that, and we got something finite and positive, which means our given series would also converge. So hopefully that makes sense. I will be back in a second. Let's take a look at this series right here, where we are taking the summation from n equals 1 to infinity of something that looks absolutely terrible. And so again, what we're going to do is we have to come up with a hypothesis here, and we have to, in order for this to happen, we have to draw upon our old Calc AB knowledge here and understand that as n goes to infinity, hopefully it makes sense that these terms here are going to matter less and less and less. So what we should suspect when looking at the dominant terms of this is that the dominant term of the denominator grows a lot faster than the dominant term of the numerator. So if I was to reduce this somehow, I could call him, the most simplified version of this, I could call him 1 over n to the fourth. And again, that's because I got that from 3 minus 7 being negative 4, which would then go to the bottom. So I'm going to go and compare to this, which is a convergent p-series because p is greater than 1. So I have now established my convergence of the series that I'm going to compare it to. And so I'm going to go and do p is greater than 1 here. So what I've got here is now, instead of trying to figure out which one's larger than the other, because now it's going to be kind of crazy, I'll go and do the limit as n goes to infinity of 3n cubed minus 2n squared plus 4 over n to the 7th plus n cubed minus 3 divided by 1 over n to the 4th. And what that gives me is it gives me the limit as n goes to infinity of 3n cubed minus 2n squared plus 4 over n to the 7th plus n cubed minus 3 times n to the 4th over 1, which I'm going to move down here. It's going to be the limit as n goes to infinity of 3n to the 7th, that's an n, minus 2n to the 6th plus 4n to the 4th over n to the 7th plus n cubed minus 3. That gets me 3, which is positive and finite. Now again, why does this work? Even though I'm getting 3, and I know what you might be thinking, like, wait a second, but that means that one series is 3 times larger than the other. Well, again, if I was to go the limit as n goes to infinity of 3n cubed minus 2n squared plus 4 over n to the 7th plus n cubed minus 3, again, over 1 over n to the 4th, if I know that equals 3, that means that one does in fact grow 3 times larger than the other. But if they converge, then multiplying something by 3 doesn't make it suddenly unconverge, right? We've seen in the past, the only way to make something that was otherwise convergent divergent is to interact it with infinity of sorts, which definitely 3 is far from that. So because 3 is finite and positive, we can conclude then that the summation from n equals 1 to infinity of 3n cubed minus 2n squared plus 4 over n to the 7th plus n cubed minus 3 converges by limit comparison. So hopefully the comparison test makes sense. Again, the hardest things about this is having your own hypothesis and figuring out what you are going to compare your series to. But it just takes practice. Usually, try to think of like p-series, integral test, and geometric series. Those are going to be things that you're going to want to compare it to. But hopefully it makes sense. As always, please leave comments or questions in the comments area. I will see you all in the next episode.